inside the system, this led von Neumann to say that the measurement chain ends only when knowledge of the measurement is registered by what he called an extra-physical factor, something outside the physical world. So some physicists today, actually many physicists today, don't like that idea because they're physicists. They study the physical world, so how can you have something outside the physical world which is interacting with the rest of it? It doesn't, it's disturbing for physicists to think about that. So von Neumann was actually saying then that in order to stop this wave-like chain and turn it into the world as we see it, you need something else, the mind. Not the brain, not the eye, but the mind itself, the non-physical thing that is you, your subjective sense. And von Neumann was not alone. Actually, almost all of the founders of quantum mechanics, these are all these famous people who started quantum mechanics, they all basically came to the same conclusion, that there was something very peculiar about consciousness that doesn't seem to be captured by what we know about physicality that was important, the way that the quantum world turns into the actual world. So these guys are all basically 1900 to about 1930, but the process went on. These are the later developments of quantum mechanics, all the way up to the present day, and you can still find many physicists who are puzzling over how do we get this strange mathematical equation which works so well. I mean, all like 30% of the world's economy depends on the equations being correct. The computer is made out of quantum mechanical stuff.
You don't have consciousness, then you don't have free will for the same reason. Everything is determined by particles, by mass. It's all deterministic. So what kind of free will can you have in a deterministic universe? And if it's all particle and material based, it must be deterministic. You just have a rule set and everything follows the rules and so on. So this big effort to get rid of consciousness and get rid of free will is really an effort to save the belief of materialism, because those things reject materialism. So that's kind of what's motivating that. And most of our scientists, most of our left-wing technocrats are materialists. That's what they've grown up with. That's the belief they were weaned on.
We are. All right, now in this learning lab, to make it more useful and more educational for us, you need feedback. In any good schoolroom, you need feedback. And one of the feedback, there's several feedback mechanisms, and one of them is that our intent modifies the probabilities in this future probable database. So we can actually have some influence on what happens next based on our intent. And then, of course, if it happens, then we live with that. So it's like you kind of create your own reality in that sense. But it's a multiplayer game. You don't create everything. It's not that you're a lone center of the universe and everything's created for you. It's a multiplayer game. So then that gets back to the double slit. So everything then is just probability before it becomes the present. Everything in the future is probability before it becomes present. In the present, then, that's where we are. Things happen, we interact, and we make choices. And then after that, that becomes part of the past. And that's also probability. So the future is everything that could possibly happen and the probability that it might. The past is everything that did happen, which is our history thread, and everything that could have happened but didn't, and the probability that it might have happened. You know, so again, we have all this probability simulations. So think of the idea that it's all probability until it gets to the present where we're interacting with it. So that's the system where pieces of that consciousness, and we're helping the larger system evolve as we evolve, because if we lower our entropy of our consciousness a little bit, the whole system, we're part of that system, so the whole system lowers it a little bit. So it's just a natural evolving system that, you know, survives by lowering its entropy, by not letting its entropy grow, which means move toward randomness. And we're just a piece of that. So then you have particles, their probability. That's just their natural state as a probability distribution until they need to be rendered in this multiplayer game. Well, in a multiplayer game, every player in the game gets their own unique data stream. So if you're working a player on the game, you're getting the data unique to that player, to where they, where they are, what they're doing, where they're looking, that sort of thing. So every player gets a unique data stream. And that's the rendering. Once something gets rendered to you, then that's information that brings that into this reality frame. Once it's in the reality frame, it has to stay here. We can't look at it this way and, we're in California and then look again and now we're in Florida or someplace. Once you have a historical consistency constraint on it, otherwise it would be a kind of a crazy funhouse reality that wouldn't make sense, wouldn't be a good learning place. So once you measure it, that brings it, or in quantum mechanics talk, it collapses the wave function, brings it into a piece of data that's now in this virtual reality. So then it has to stay that way. So if you look at the double slit as information, and you realize that it's not really the measurement, it's not the consciousness, although it takes a consciousness to make a measurement, it's really the information. And once you see that, you can predict all the results of all the different kinds of double slit and the erasures, and all of that just fit perfectly consistently, and it makes perfect sense. You know how you have the trying to think of what that experiment was called. Anyway, in about 2000, there was a group of researchers who did a very neat double slit experiment where they had particles came into a plastic that then, when the particle hits, it puts out two. So you get an entangled pair that come out of that. And then they use one hits the screen and decides whether it's where the particles land, what the distribution is. The other one, its twin, goes through another process which either will or will not determine which slit it went through. But it doesn't make the first decision in that process of which slit it went through until after the other one's already been captured and it's a done deal.
Yeah, it's a late choice.
Yeah, it's a late choice. Yeah, so it's erasure basically. It's you have erasure experiment. So you have captured this data, then some 10 nanoseconds later, but 10 nanoseconds or 10 years really doesn't make any difference. Right. Time's not the issue. You make a choice over here, or it makes the choice, not the experimenter, but it makes the choice, depending on how it goes through a half-silver mirror, or several of them, as to whether it keeps the information and says what slit it went through, or erases the information and doesn't have it. And of course, then you look at all the points, and all the ones where you kept the information, what slit it went through, all the slits that correspond to that one that you collected up here are all two little spots behind each slit. And every time that you erase that information, you get a distribution that's in a diffraction pattern. But they don't have a clue as to why a particle should be a probability distribution to begin with. That's just an accepted, well, that's the way it is if you want to get the right answer, but there's no explanation. And
so in a sense, it's as though we're living in the movie The Matrix. Mm-hmm. Right? I mean, that's a sort of virtual reality that.
Yeah, that's a good Hollywood version of that, right?
So then, what comes to mind is the old parable from Plato that what we see of the world is a projection of something behind. Just like looking at the movie The Matrix is Plato's cave all over again.
Sure.
It also suggests that it should be possible to create an actual simulation on a computer that would demonstrate a lot what you're saying,
Exactly.
because the metaphor is very close. Could be simulated.
Yes, it could all be simulated. You create the environment, and it will become conscious. It's not a matter of here's how we program consciousness, because as soon as you try to do that, you've restricted it to the algorithms, and now you have some kind of deterministic thing that can't do anything but go through your code and come up with the same answer if you give it the same inputs, and that's not consciousness, you see. So we have these real slow responding things called bodies. They're electrochemical, they're physical, they're levers and tendons pulling, muscles pulling on tendons that pull up arms. So you have levers, you have fulcrums, you have electrochemical things that get emitted by this gland and it moves down here and does something else, so that you have these very slow processes compared to the system which runs these delta T's at about 10 to the minus 44 seconds per delta T. So that's small. That's like, what, 4 orders of magnitude? No. Something like 30 orders of magnitude smaller than the smallest thing we can measure. So it's real tiny, 10 to the minus 44 seconds. So that's kind of the computation time, if you will. But now you have these very slow-moving things going on. So there's a little video lag problem between the data stream and the action. I had an engineer friend of mine who have said that it was very straight. If you can't measure it, it doesn't exist, or it isn't important. And he one night had a dream where he saw an airplane full of people. He was a kind of engineer that understood airplanes, and he knew the makes and the models and those kinds of things, a technical guy. And he saw this airplane. He says, "Oh, that's a such and such a make and model," and he saw the people on it. And it was maybe 100 people. And they were all in black and white except one little girl who was in color. And he looked at them, lots of detail. He says, just as much detail if he was there. It wasn't a dreamy kind of foggy thing. It was precise, like photographic. 2 days later, a plane crashed. Everybody was killed but one little girl. Same plane, same make, same model. And at that point, his life changed. You see, he became interested in finding out more about the larger reality. Mm-hmm. Just like the double slit is when you actually take the measurement, which means you go add up what's the average number from these streams of random numbers. That's when you collapse, the wave function and get a result that's now in this physical reality. Before, it was just a probable result. You see? Mm-hmm. So you can arrange, you can change the constraints on it in a number of ways to show that what's really going on here is that you have a digital reality. You're modifying the probability with intent, and as you put constraints on it, they can do different sorts of things. Mm-hmm. If you look at the average of the ensemble, then they can change all the ones in between, but over the whole, it's got to hit that number that's already been collapsed into this reality frame. So that would be a whole set of experiments, not too hard to do, that would kind of show this process.
And then
Now, this idea of a multiverse is not gratuitous speculation. No, it really comes out of both experiment or observational physics about the universe and the current theories as best we understand them.
vantage point.
I don't have a single colleague in science who thinks that space actually ends here at the edge of our universe. Where it starts getting more controversial is when you ask, well, how much more space is there?
Way of knowing. One interpretation of quantum mechanics, which I think makes a lot of sense, says that when the photon hits the polarizer at 45 degrees, there's actually two futures that happen. One where it goes through the polarizer and one where it doesn't, and each future continues as if the other future were not there.
In the many worlds theory of the multiverse, the entirety of the universe acts like the quantum photon, but instead of having two potential future states, every possible outcome would be manifested. So our entire universe, and everything within it, including you, would be constantly undergoing multiple fissions into daughter universes, each with its own reality and future. Any given observer, though, would only see one outcome.
I think the jury is still out on whether there's a multiverse. It's odd that some people get very emotional, some people are very hostile to the idea because they don't feel we should talk about entities that we can't directly observe. I think we've got to be open-minded because we have good theories which predict that the multiverse must exist. And I hope that we can settle this. I think it's an empirical question.
Taking a step back, I mean, it's proven very difficult, surprisingly hard, to come up with a theory of physics that predicts only what we see and predicts that there's nothing else.
I actually don't think it's that mysterious. We live in a world that's full of stuff, and this world happens over and over again with the stuff in slightly different positions. Time is just the label on all those different moments that constitute the history of the universe. It's very much like the page numbers in a book. Einstein tried very hard. He worked for 10 years after inventing special relativity to fit gravity into the framework, and eventually he realized he needed a new framework. So he invented what we call the general theory of relativity, where Einstein says that this space-time stuff, this four-dimensional world in which we live, has a life of its own. Space-time itself can move. It has dynamics. It has curvature. And it's that curvature, that geometry of space-time that you and I experience as the force of gravity.
And then he found that time was also changed by your proximity to a very massive object. So like
in the sense that, although people don't admit it, they say that the main purpose of physics is to calculate the results. You see, what they say is that when students first take quantum mechanics, they find they can't understand it. And about a year later, they say there's nothing to understand because it's just a system of computation.
So now I don't understand that. I mean, are people now getting so much into their machines and their analytical tools that the numbers they get out become all important rather than the phenomena there?
That's on one side, that's part of it. See, it's confused because on the other side, people firmly believe that they're going to find the fundamental building blocks of the universe. They feel they're really real, but when it comes to discuss what they mean, they then say, well, they don't mean, they're just computations. You see, I think people haven't thought out the full. Each person does his little bit, the fragments, and each person does his little bit and doesn't worry too much about what's beyond. And he may perhaps assume that somebody else has taken care of it. And so the whole thing just goes on without people generally worrying about what the whole thing means. these electrons connected at long distances. So with that absolute contradiction of the two basic theories, I said we could try to find out what they had in common. Now what they have in common is what I call undivided wholeness. You see, the view of relativity which Einstein was pursuing was that that there's only a general field. Particles are concentrated regions of field which spread out through the universe and merge with others. So the particle is an abstraction, according to Einstein. There's only a whole field which is undivided, right?
All right.
And that's the undivided wholeness is what characterizes that theory. Now, quantum mechanics, in a very different way, comes to the same thing, because it says energy exists in the form of indivisible quanta, and the entire movement of the universe is made up of unbreakable, indivisible links, you see, and which include the observer and the observed. Let's see, it includes us as well as the atom we're looking at. And so relativity and quantum theory both agree on that. So I said that would be the starting point, to start from the whole and to say the parts are abstractions from the whole. They have no independent existence. Now I think you can get a simple image of that if you look in water and see a whirlpool or a vortex. See, it looks like an entity, but it isn't. It's nothing but a constant pattern of movement in the water. If you put another whirlpool in, the two penetrate each other, merge, and produce one new pattern. They do not produce two separate whirlpools interacting.
Me, that there is this interconnection. But what about the vast spaces of outer space that connect various bodies in the heavens? Are you implying...
No, that too, yes.
That too?
Yes, to say that as the field spreads, you can see immediately the field spreads. See, light is also carried by this field, so the entire universe is connected through that field. Electric fields, light, various forces are carried, gravitational forces. And so that space is merging with matter. Matter, in that view, is a certain property of that space which is a bit more concentrated or something.
Okay, but you implied there that there is a wholeness.
Yes.
And yet it seems to me that certainly I have the conceit to think that I'm an individual, that I have my own uniqueness and individuality, and I run around, and what I do here has no real connection with anyone else.
Well, that's an abstraction. You see, if you just think a little while, you'll see it can't be true what you've said. You see, you're surrounded by air, water, and so on, and if you were not surrounded in that way, it wouldn't last very long. Now, also you're surrounded by people who feed you and keep you alive, and also give communications which keep your mind going. And a person totally isolated would never even be human, right? Now, so I think just a little observation shows that view is not really true. That at best it holds as an abstraction. Now, also materially, see, if you take waves passing up through a pond, they pass right through each other, right, as if there weren't any. But if you put a rock in there, you see the rock scatters the waves, so the waves would show up that rock. They wouldn't show each other up, right?
Folded and unfolding. Do we have the tools to...
Well, at present I have to begin with this. In one sense, I'd say experimentally, that's just what our electrons are doing. You see, they're behaving both like waves and like particles, but our language doesn't, call attention to that very well, but tends to talk about building blocks all the time, and prevents us from thinking that way. Now, the mathematics of quantum mechanics does, which is a certain kind of algebra, does actually describe that, and I'm working on that to make an extension of that mathematics, so that we could make a picture in which the mathematics and this particular way of thinking would agree. And it can be, first of all, investigated mathematically, and then eventually, when the thing is developed theoretically, and when it is developed far enough, it might lead to some new experiments.